So yesterday we talked about the main operating principle of the brushless DC motor, okay, which is summarized in these two slides, this one and this one. We have 6 operating modes in which just 2 legs out of 3 of the standard 3-phase inverters are, let's say, activated. The remaining one is left open, so no current can be, say, can flow through the left open leg. And for example, you can see that you can have in the operating mode number 1 a current which is flowing inside the node A. So we have the current flowing here and then exiting to the, say, leg to the phase B. Okay, so we have the situation that I called A plus, B minus, okay, because the current enters A and exits B. So in this situation, we have to close, for example, transistor T1, okay, the high side transistor of the leg A, and then we have to close the low side transistor of the leg B. So in that situation, we have a current that flows exactly in this way here, returning to the VD source. So the current I flowing through the 2 phases, A and B, is the same current that flows through the supply, okay? Is the same current flowing to the transistor T1, etc., transistor T6, returning to the leg. Then we have a situation, operating mode number 2, in which we have to switch from A plus B minus to A plus C minus. In that situation, we have to activate the T1 transistor in the leg A and then the transistor T2 in the leg C, while the leg B is left open, etc., etc. Okay, so we have this typical situation that you have to, say, manage in order to consider the operation of the brushless DC motor. In the same discussion that we had yesterday, I also stated very briefly that similar to a DC motor, the speed of a brushless DC motor is proportional to the voltage applied to the motors. Okay, so for example, if you have a, say, modelization of the brushless DC motor input electrical port in this way, for example, this is just for the phase A, RA are inductance and the ohmic losses for the phase A, and this is the AE back EMF of the phase A, then the speed, which is proportional to the back EMF, is somewhat proportional to the voltage that you applied between this phase, okay? And so it means that if you are changing the voltage V, basically you are changing the current flowing to this situation. This is exactly the same operating mode that we had for the brushless, for the DC motors, okay? In which you can modulate the voltage in order to change, say, the current high flowing through the phase and make possible to have the operating speed you need for, say, that specific application that you are working on. So if you look at the situation I just depicted before, let me just to, say, summarize, for example, the situation for the A plus B minus, the operating mode number 1 I discussed with the slide before. You have transistor T1, okay, and then you have the node A, and then you have, let's say here, the node B, and the node B is connected to here. And so these 2 switches are closed, and so we have a current I flowing here, entering node A, exiting node B, going here, and then it's returning here. The third phase, which is C, and it is connected here, is left open because the phase C is not, say, connected to anything. The two switches here are open. Okay, so this is what happened in that situation. So what is the voltage that, for example, you have from the node A and the node B? This voltage is exactly the voltage VDC or VT, the input voltage that you have here. If you want, you can refer this voltage to the center, say, of this star connected load here, and then basically what happens here is the voltage is, let's say, constant. Okay, so this situation is typically in contrast to my requirements. Okay, I have to modulate V, the voltage that I supply to any phases, in order to, let's say, make possible to modulate, to control the operating speed of my BLDC motors. So in that situation, I have just constant voltage. So typically, what is done is to apply, say, pulse width modulation techniques, by which I can use as, say, supplying voltage for my phases an average value, which depends on a duty cycle. Okay, so what is done is pulse width modulation is employed to modulate phase voltages in order to make possible to control, by means using a average voltage, say, averaged by means of the duty cycle, the phase voltage, and so to control the operating speed. Okay, so this is not the situation that we have to face. Typically, these two switches are, say, modulated on and off in order to make possible to change the average values and to change the voltage applied. Okay, this is something that with the typical operating situation. So let me just describe very shortly in which way I can control this operating speed. Okay, just to say, to see a schematic description what can be done for BLC motors. We have this inverter. Okay, this is the DC side of the inverter, in which you have the CD capacitance. This voltage is called in the slide, and I call it the same way, VDC. Then I have three outputs, A, B, C. Okay, they are, say, connected to my DC motor, so I don't know how to describe. Let's see. This is the shaft, so we have an operating speed here. This is my BLDC motor. So since I'm using a pulse width modulation techniques for changing the average value of the phase voltage, and so to change the operating speed, I need a modulator, okay, which is the standard modulator that we can use for, say, any kind of three-phase inverters. So we have here a unit switching function that drive the operation of the switches in the leg. I have to measure the operating speed. Okay, so this operating speed is measured, and so we have some, say, sensors that make possible to measure the speed. Here I have a speed controller that has this information in real time. Here I have a reference. This is the reference speed, so the speed I want to get at the output. This speed control generates a current. Let me call this current I star, because it's a reference for the current controller. The current controller has this reference here, and so we have to, say, inside the current controller, compare this reference current with, let's say, the current that flows through the phase. But look at this description that I have here, which is the current that flows through the phase. The red, say, path here is followed by the current I. Okay, here you have a current I flowing through the phase, which is the current flowing in the DC side. Okay, so basically, what kind of current you have to monitor to, say, make this comparison? The current flowing here. The current I is measured by this sensor. This is a current sensor. The current sensor provides the actual current I. This is compared with the reference current, which is the output of this speed controller on the basis of a reference speed and the actual speed measured at the shaft of the motor. And then this current controller generates the control voltage. This is the control voltage for the modulator, for the pulse width modulator. Okay, and so in that case, I can have, let's say, the control of the operating speed. This is the typical architecture for, say, controlling in an accurate way the rotating speed of the motors, the BLDC motors. Okay, of course, this speed control are some parameters like the proportional constant of the speed controller, the integral controller coefficient, etc. So you have here a PI controller, for example, in the same way we did for the DC motor control. And the same happens here for the current control. So you have, say, another PI controller. So let me just to discuss in a little, with a little bit of more details the pulse width modulation. Okay, I said before that in order to, say, control in accurate way the rotational speed, I have to, say, modulate the voltage applied to the phase, and this can be only done, for example, or it can be done in an effective way by using, say, a technique which is the pulse width modulation. Okay, so I have a duty cycle by which I can control the switch on and off operation, and so I can play with that duty cycle in order to get at the phase input an average value which can be controllable. Let me just to discuss in which way you can use this pulse width modulator, because in BLDC motors there are typically two different ways in which you can apply pulse width modulation. And in order to do that, I want to use the slides. Okay, so let me just to share the slides, because the drawing there are much better than mine. Okay, basically these slides show you that here you can see that the two basic techniques, pulse width modulation techniques that can be employed for BLDC motors. On the left, you can see the so-called bipolar switching methods, and on the right, you can see the unipolar switching method. Basically, the names are the same that we have for, remember, the bidirectional converters, or say the one-phase inverters, etc. So you have this situation on the right in which you can see that you have the three-phase inverters, okay, and then you have the representation, the schematization of the three phases of the BLDC motors. The situation here is the situation in which the B phase is left open. The current goes to the phase A, so we can see that the current enters here. So we have, sorry, the current is exiting according to the direction of this current here, this I current here. So we can see that this is a C plus A minus situation, okay? C plus A minus. So what does it mean, C plus A minus? Remember that you have this one, the phase number 5, okay, is there represented, okay? In that situation, according to this schematic configuration of the switch, you have T5, which is, say, closed. So in order to have the current I flowing through T5, enter C, exiting A, and T4 is also closed. Okay, so T5 and T4. T5 and T4 are closed. Now move to the bipolar. So we have this transistor here and this transistor here, T5 and T4 are, say, to be switched. Okay, in the pulse width modulation, these two switches here are not closed for the entire intervals of the operating mode number 5. They are switched on and off according to our pulse width modulation patterns, and so it means that when you switch these two transistors here, you have also to switch the opposite transistor in the same leg in order to avoid, say, the cross conduction. Okay, so the transistor in the same leg, for example, this one, T1, and this one, which is, say, it's T4, yes, must be switched in a complementary way with respect to the other two. Okay, so I'm providing a pulse width modulation command to the two transistors that I want to activate. So T5 here and T4 here. Okay, the other two transistors in the same leg are, say, complementary switched. So what happens in that situation? Okay, that situation basically applied pulse width modulation to the two transistors that they have to be closed. Okay, what is the voltage that you can have between the phases? Okay, so let me consider this, say, topic here in the whiteboard. Okay, you have the situation which is the following one. I have this transistor here, which is T5, which is closed on and off. This other transistor here, this is the leg C, as a complementary, say, action. So when T5 is closed, T4 is open, etc. The leg B is always open, B open. And then you have the transistor T4, which is pulse with switched modulated. And then you have T1, which is operated in a complementary way with respect to T4. So here you have the phase C, which is here. And then you have A. Okay, this is the operating mode number 5, which is called A minus C plus. Okay, the current I, which is the current flowing here, flow basically following this pattern, something like this. The voltage that you can have between these two phases here, so VCA, is a voltage that can be when T5 is, let's say, T5 and T4 are both closed, then you have VD. It means T5 and T4 on. When they are open, then T1 and T4 are, sorry, this is not, this is T2, sorry, T2. When T5 and T4 are open, then it happens and T1 and T2 are closed, and so the voltage is totally reversed. So from VDC to negative VDC. So as you can see here, there is a situation in which effectively you have a voltage which is, let's say, bipolar one. Okay, so this is the bipolar pulse width modulation techniques. So basically, this voltage can be, say, you have to take the average quantity, so you can have, say, the filter that is represented by the motor itself, and so the effective voltage averaged is something which is related to the duty cycle by which I'm having this, say, commutation, etc., like in the standard pulse width modulation inverters. What are the advantages of this pulse width modulation? Remember when we talked about the, say, the polar pulse width modulation, okay? And also remember what we said about the stepper motors, okay? Remember that I said always that anytime you want to make faster transition, then, and you have an inductive load, then you have to put the maximum negative voltage across, for example, the inductive load to make faster turn off, or maximum positive voltage across an inductor to make the current rising, so to turn on. In that situation, you have exactly that situation, because you have a, say, a peak-to-peak voltage ripple, which is 2 times VDC. The negative voltage is the largest as it possible, so negative input supply voltage, and the positive one is plus VDC. So in that situation, you have, let's say, a very fast transient response. Remember that, for example, in the stepper motors, okay, we modified a little bit the driver, the L over R or the R over L driver for stepper motor, in order to get negative positive voltage across the inductive load of the stepper winding, introducing the chopper driver that has exactly this behavior. So this is reversible in voltage, so in order to make faster transition. So this is always happens when you have bipolar transition, bipolar modulation. What are the drawbacks? The drawbacks is that something that we already know. When you have a bipolar commutation like this one, then you have a very large current ripple. Okay, so and then what happens? Look at this. The phase B is not indicated here, but there is a phase B which is left open. But look at the phase A. See that that phase are activated. Then you have 4 switches that commutates. So you have large dynamic dissipation. So this is the reason why you can also use another different pulse width modulation techniques, which is the unipolar one. In the unipolar pulse width modulation, supposing that we have the same phase as before, the phase number C, which is A minus C plus activated. We have VDC here. And then you have, say, the phase B is not activated, is left open, so I'm not drawing it. Then you have T5 and T4 here. This is C. And then you have A phase. Okay. In that situation, the voltage VCAA can be obtained. So, okay, I have to say, considering these 2 transistors, my, say, number 5 operating step. The pulse width modulation is just, let's say, for example, applied to T4. So it's T4 that goes on and off following a pulse width modulation patterns, okay, depending on the duty cycle, etc. T5 is always closed. Okay, here is always closed. So always on during T5, of course. And this is pulse width modulated. So, which is the voltage VAC? Of course, when this is modulated, the transistor T1 is also modulated in a, say, complementary way with respect to T4 in order to avoid the shorting the VDC source. What about VAC? For example, in time domain, we have that when T4 is closed, then you have that this is VD, VDC. When it is open, it means that T1 is closed and then the voltage is null. Okay, so in that case, you have no more a bipolar variation, but the voltage applied to the phase, say the line-to-line voltage you want, but then you have just unipolar. This means that the minimum voltage to apply to your phase is 0. So in terms of, let's say, transient response, of course, this solution is slower than the bipolar one. Okay, but what is the always good feature of unipolar pulse width modulation? They have smaller current ripple. What is another benefit of having unipolar modulation is that look at this condition. At the frequency TS, so the switching frequency, now are just activated 2 switches here, the switches of the leg A, while the leg B has just 1 switch, but is always closed in that phase. So here we have low dynamic dissipation. Okay, so if you count the benefit of the unipolar pulse width modulation with respect to that of the bipolar one, you can see that unipolar has, say, large benefits, okay, in terms of, say, small current ripple, so the smaller torque ripple, and then low power dissipation. So that means that typically most of the time the pulse width modulation technique which is employed for brushless DC motor is that unipolar one, okay, the unipolar pulse width modulation. Then this unipolar pulse width modulation has several different, say, sub techniques, if you want to call it this way, that are employed to specifically solve some problems that can be arise. For example, the current that circulates into the not activated phase when you have, say, this operation mode. Okay, there is a problem that is the current flowing through the phase B in this situation, through the body diodes of the transistor that are not activated, and so this can be a problem. Okay, I don't want to say specifically detail these issues, but basically you can solve this by modifying a little bit the way you are activating the switch. For example, there is a situation which in my discussion here, I apply the pulse width modulation pattern to this transistor, then T1 is activated in a complementary way, and then I close T5, okay? But there is also the opposite situation, which I activate the pulse width modulation to T1, to the high-side transistor. T4 is, let's say, complementary way activated, and T5 is always closed. Or there can be the situation in which you can divide the interval operating mode 5 into different half. In one half, you can have, for example, this kind of situation. In the second half, you can reverse the operation. So there are a lot of different, let's say, way to face this problem. So you get the same result, but with different switches that are activated. This is shown in the slide if you want to look at these different behaviors here. that are called upper switch pulse width modulation, lower switch pulse width modulation, ongoing, off-going pulse width modulation that are typical for unipolar switching method. Just for say understanding, let's say the upper switch pulse width modulator. Let me consider what happens in the phase that we call number 5. Okay, the operating mode number 5 is A minus C plus. So here's something that happens here. This is the operating step number 5 that I discussed briefly before. In that situation, I have that in the upper switch pulse width modulator, I apply pulse width in the phase C, so to the transistor T5, and I close the switch T4. Okay, so in the situation that is say reverse with respect I discussed with you before. Now the switch which is always closed is T4, but I apply pulse width modulator to transistor T5. Or you can have lower switch pulse width modulator in which the same operating mode here, A minus C plus, which is here, is operating in the way I showed you before. I apply the pulse width modulation to T4 and I make, say, T5 closed. Okay, so this lower switch pulse width modulator is exactly the operating mode I discussed, I graphically showed you before. I applied pulse width modulation to the lower switch, so T4, but I always make closing, make on the transistor T5 in the leg C. Or then you can have a mixture of the two situations that I showed you before. You can have A minus C plus, for example, activating in half the period the switch is closed, the other half the period is, say, is pulse width modulated, etc., etc. So you can get the same results. There are a lot of research in doing some specific modulation techniques to solve some specific problems that you can have. But this is something that is, say, far from the goal of this course, but just you know, okay? Remember the discussion that I have here, okay? At the beginning of this, say, brushless DC motor, say, operating principle discussion, I said that in order to make, say, to generate a continuous torque at the output shaft of the brushless motor, I need to know the position of the magnetic field generated by the permanent magnet in the rotor. And this action is performed by using specific magnetic sensors that can be, for example, the Hall effect sensors. And in this explanation, I put H1, H2, and H3 in that specific configuration of three-phase and two-poles BLDC motor that are shifted by 120 degrees, and they providing a useful digital signal that can be used to, let's say, generate the control signal in order to understand which is the correct phase I have to energize. Okay, so for example, this discussion is made here by considering which of the two of the three Hall effect sensor are say activated, etc., etc. So we need this kind of Hall effect sensors. However, the position sensor of the position of the rotor increase the cost, increase also the size of the motor. And anytime you add something, then you reduce the reliability of the drive system, okay? Because you have another, say, mechanism that you have to control, you have to be sure that it works correctly, etc. Remember that the original goal that make possible the development of a brushless DC motor was to change the architecture of a DC motor, avoiding brushes, mechanical fixture, etc. Now I'm discovering that in order to make, say, to generate a continuous torque, I need to add something. I can avoid the brushes and say the commutators, but I have to add Hall effect sensor. These are, say, semiconductor devices, though they are not so unreliable like the brushes or the mechanical commutator that you add in the DC motor. But anyway, the cost is, say, a little bit, say, increased. And so certain research is made in recent years to make the brushless DC motor to be operated without using all effect sensors. This is called the sensorless control of brushless DC motor. How can you, say, control, how can you choose which of the three legs I have to energize and which one I have to left open by not using, say, the brushless DC motor? So look at this slide here. Okay, this slide here, another time, show you the 6 operating modes in sequence, 1 to 6, show you the back EMF for the phase A, the phase B, and the phase C, and the current flow through the phase. Okay, exactly the same explanation and description that I have. This kind of operation mode is performed, in my previous explanation, by looking at the position of the rotor by the all effect sensor. Now, suppose that I want to get the same behavior, but without any information about the motor. How can I, say, get the rotor position information without using the all effect sensor? But basically, there are a lot of different methods, okay? But one well-known method is called the back EMF based method, okay, which is described here, back EMF based method. So this method looks in details the back EMF evolution in time, okay? And specifically, what is, say, under evaluation is the back EMF of the phase which is not energized. So suppose that you are in the operating mode number 1, okay? And then you have A plus B minus. So I am energizing the phase A, the leg A, and the leg B. The leg C is open, is left open. So the leg C is here. Open phase is C in operating mode number 1. What is the behavior of the back EMF of the left open leg? Now look at the back EMF of the phase C, which is the leg which is left open, is this one. Now focus attention on the, say, operating mode number 1, which is the first sector in this evolution. And look at the phase C, which is here. The back EMF has a transition, okay? The open phase has no fixed back EMF, okay? The back EMF is constant only for the phases that are energized, A and B here. For what concerns the open phase, the open leg, the back EMF has a transition between, say, a positive value in this case and a negative value, okay? And it has also a, say, points in which the back EMF crosses 0. Okay? The arrow here indicates exactly a time instant, or if you want, an angle, a position of the rotor, in which you have transition from positive back EMF of the phase C to negative. Okay, there is the cross of the 0 value. So in that situation, you can see that you can recognize that each of these phases, this operating mode 1, 2, 3, etc., lasts for 60 degrees of the rotational speed. Okay, there are 6 in one complete revolution, 360. So each of these operating mode lasts for 60 degrees of the rotation of the rotor. So this width here is 6 degrees. This arrow here, this crossing of the back EMF of the left open phase happens exactly in, say, exactly half this interval of 60 degrees. So we know that 30 electrical degree after the back EMF crosses 0, we have to change the operating mode. And this happens always. Look at the operating mode number 2. Now we have A plus C minus activated and B is left open. Oh, sorry. Here. B is left open in the operating mode. Look at the back EMF of the operating mode of the B, which is in the mid drawing here. Then you have, let's say, another crossing point, and 30 electrical degrees after this crossing point, you have to change operating mode. So basically, if you look at the BKMF of the not activated phase, you have just to look not on the entire evolution in time, but just to, let's say, recognize when the BKMF crosses zero. When you have this crosses zero, then you have to know that 30 electrical degrees after, you have to change operating mode. So you can basically use this technique just to have information about, say, the position of the rotor at which you have to change the phase without using all effort sensor. Okay, so this is a sensorless control of BLDC motors that make possible to make the brushless DC motor to be operated without any information about the position, so without any all effort sensor. How can you evaluate this BKMF? But the BKMF appearing at the phase of the motor. Okay, so let me just discuss this circuit here, which is a schematic circuit showing you just the operating principle. Okay, I have the inverters, I have the BLDC motor, and then I have a circuit that is called the BKMF detection circuit. Okay, the circuit which is devoted to evaluate the crossing point of the BKMF of the phase which is left open. Okay, so this block here as is connected to each of the three phases. Okay, because depending on the operating motor, you have to, let's say, look at the phase A or B or C, and this voltage, the voltage that I measure, is referenced to the central point here, the star point. And then you have a comparator, for example, and this comparator, make possible to understand when the voltage crosses zero, okay, and generating a signal which is employed for, say, driving the motor. Okay, here there are a lot of problems, okay, because the voltage that is sensed, so the input voltage of this circuit, is very noisy, especially if when you use a pulse width modulation techniques. Here you don't have something which is smooth. You have something which goes from 0 to VDC and going to 0 again, or negative VDC to plus VDC, which are frequency which can be large. Okay, so this means that this voltage here needs to be low pass filtered. Okay, you have to get the average of this value. So inside this block here, there is a low pass filter that may be possible to, say, takes just the average in order to get, say, this. But when you have a low pass filter to, say, avoid the transition at the switching frequency, remember that any time you have a low pass filter or filtering action, then you have also a delay of the voltage or the current you are sensing. And in that specific situation, anytime you have delays, you have an error, okay, because the delay is exactly what you have to measure. Okay, if you are, say, measuring this voltage here, for example, in the operating mode number 1, but then due to the low pass filter you need for avoiding the pulse width modulation switching frequency, and then this point is delayed by the filter, then you commit an error in the switching action. Another error is due to the fact that typically, okay, in typical, say, application, the circuit that is devoted to detect this crossing is a low power signal, okay, is an integrated signal, an integrated circuit. And so the voltage level are not compatible to maybe the voltage that are applied to the motor, depending also if the motor is applied for industrial applications, so you have large voltage applied to it. So you have to scale the voltage here. You have to make the voltage level to be compatible with the circuit that is connected here. And so you have to make, I don't know, you have to reduce the voltage. But what happens, for example, to the BKMF when the operating speed is very low? The BKMF here is something which is proportional to the operating speed of the motor. So when the operating speed of the motor is in very low range, okay, the BKMF is very low in amplitude. And since you are using something that, let's say, compressed the dynamic, the signal that you are measuring here is even lower. And so this very low amplitude value that you are using for low speed of the motor can be corrupted by noise, okay? And so you have another error. Then a third problems of this architecture is that You can use these for, say, getting information about the rotor position, but this is not valid when you start the motor, at the startup of your motor. In that situation, you have no back EMF because the operating speed is null. And so in that case, you have to add something else for starting up your BLT motor. And then only when the motor is starting up and then you have, say, operating speed and then back EMF, then you can use this technique here, okay? So I just want to put on the table all the possible problems, okay, for that secret. Basically, it can be employed. Maybe the accuracy of this technique is not so good, but of course, this technique needs to be a little bit improved. There are a lot of techniques by which you can do that, but okay, this is bring us too far from, say, what is I want to discuss here, okay, which is the basic information about this kind of driver from brushless DC motor. Basically, here I have, say, concluded my talk about the brushless DC motor, and at the same time, the material I'd like to, say, mention and discuss it with you for this course. Okay, I have some questions about this, what I said for brushless DC motor, something which is not clear. Is all, let's say, clear? No problem. Okay, I want to spend a couple of minutes, maybe more, for giving you some, say, description about the written examination. Okay, just to make clear what you can expect from this exam. Okay, so let me just share this whiteboard. Okay. About exam. As you well know, the examination in a situation which is not pandemic like today is just an oral examination, okay? But we have no information about what will happen in the next week, so I think that we have to choose, let's say, a remote exam, okay? So I have to choose for the, say, pandemic examination, let me call it this way, which is a written exam, okay? So is a written exam. And a written exam without the help of the books or notes, whatever. So it is a, say, closed books exam. This exam will be performed by use virtual classroom, okay? In the same way you connect to the virtual classroom for today's lecture, for example, in the same way you can get the connection for the examination. Okay, I will start a virtual classroom. Okay, this virtual classroom is just for examination. Okay, so people that are, say, they booked for the examination can have the link for getting this virtual classroom. I can use Zoom, for example. Okay, it's not a problem. And no, so some exoteric tools for controlling you. Just say you need a webcam and of course an internet connection for making this exam. Okay. So is performed by virtual classroom, for example, by Zoom or with other whatever other tools that makes possible to see you. Okay. What you need for this examination? That you need webcam, connection, of course. You need, let's say, papers, pen, and stop. Okay. No books, no notes, no friends. Okay. I have to see you. Okay. So that means that, for example, let me just to share the video. You should see me. Okay. I'm here. Okay. The frame for your webcam should be something similar to what you can see now in your in your screen. Okay, I have to see your face. Basically, say if you are talking with someone, I have to see your face. Then you need a paper. Okay, and what I have to see that you are, say, writing in your paper. If you have a cell phone, the cell phone must be put, say, face down here, close, and then you can answer your question. Okay, I will share the questions for this written exam by using, say, the tools that are provided by the, for example, Zoom. Okay, in order to share the PDF file, so you can see your PDF file, then you can say have your question to this sheet of paper. Then at the end, you have to, let's say, scan your answer, and then you have to upload to the Elaborati section in the student website of the course, Advanced Electronic Drive. There is an Elaborati section. Okay, so let me just to write down these notes. Webcam, framing, face, ends, and papers you are writing. At the end, scan your answers and upload to Elaborati section. Okay, in order for me to download them and, say, correct them. Okay, is it clear? So nothing difficult, I think. Okay, it's something that is, say, can be performed in this way. Now I want you. How can you scan the answer you have? For example, you can use you can make picture, for example, using your phone, or maybe you can use some specific tools. For example, there is the Polito app that has a specific feature that makes possible to, say, scan, to generate PDF by just framing your papers, and then you can, say, upload to the Elaborati section. Before getting the examination, say, try some experiments in order to see which is the fastest way to scan your documents in a PDF. Okay, so then I want you be a little bit more precise about what you can find into your examination, because I had some variation with respect to what I previously explained, I previously mentioned in the first lecture. Okay, in the first lecture, I have this kind of examination, pandemic situation, 1 hour written exam, 3 questions. I put here old because I changed a little bit, and so new from, say, this section and for all other section is that I have 1.5 hours, so half an hour more, always written exam. The 3 question was previously open question. Okay, now I put say 2 open questions and one part composed by, let me say, 5 to 10 small questions. Okay, so 2 open questions, exactly the same kind of questions I have in the old, say, written examination. 2 open questions means something that starts with the words describe, illustrate, explain something. Okay, illustrate, I don't know, bipolar pulse width modulation for, I don't know, one-phase inverters. Of course, a similar question requires that a premise. Okay, you have to illustrate what is a one-phase inverter, the which way, the operating way it works, the derivation of the, say, average value of the output, and the way you can have a bipolar pulse width modulator, the benefit, etc. Okay, so it's an open question. Okay, whatever you know in order to fully describe what is the answer for that question. Okay, not just say pulse width modulation. Bipolar pulse width modulation means that you have just, say, 2 values at the output and stop. Okay, of course this question here should be longer because I put some steps. Okay, describe one phase inverters as a first question, describe the operating mode in I don't know, bipolar pulse width modulator. What are the advantages with respect to other kind of modulation, for example? Okay, so if you follow, attended all the courses of the lectures, you have no problem at all, because I'm just want to ask what I explained. No surprise. Okay. The other part here, which is composed by 10 or less, 5 to 10 small questions, are something that you can answer in just, say, few words, or say few lines, 3 lines. Okay. It's not a long explanation. Okay, because the question will be very specific. Okay, if I ask you which is the maximum ripple in the current that you can get for a bidirectional DC-DC converter, this is a question that has just, say, one expression, the maximum ripple value in terms of voltage, in terms of inductance, whatever. Sometimes I can put here also questions in which you have to choose between different alternatives. Okay, so you have just to put, I don't know, there are a question that asks which one of the following sentences is the right, A, B, C, D, and then you have to choose which is the right. Okay, so 5 to 10 small questions that you can answer in a very fast way, just a few lines, just indicating an expression, just indicating which of the alternatives is right. Okay, this makes possible for me to get a more objective, say, more objective valuation of your works. Okay, because of course, a long questions can be subjected to, say, several indication, but when you have to answer some specific question, the answer is correct or not correct. There is no something which is in between. Okay. Okay, have you understand my goal? Okay, so basically, yes, I have a question here. Where are the questions? Oh, yes, here. Okay, just thanks. Remember that in this course, I made some specific part just for students in electronics and students in mechatronics, okay? Of course, these two parts will have a impact on your examination, okay? Because there can be questions that are just devoted to students in electronics and questions that are just devoted to students in mechatronics, okay? I will put typically an acronym, questions for electronic students will be indicated by these acronyms, okay? And mechatronics by MCT. So, of course, mechatronic students have not to answer the question for electronic students, etc. Okay, because they have 20 hours, basically different the topics, okay? So, for example, in these 5 to 10 questions, some of these questions can be just devoted to one of the two populations, okay, of the students. And also the two open questions. Maybe one question can be, maybe none of the two, or maybe one of the two can be just directed for electronic students or mechatronic students. But basically, all of you have to answer 2 questions, open question, and to answer 5 to 10 small questions, okay? Have you questions about this procedure? Now I want to be a little bit specific about the possibility to withdraw or not withdraw, etc. For me, you can withdraw, say, anytime. At the beginning, at the end, in between, okay, you can withdraw anytime without any, say, without lefting any sign, if you see, okay? It will be indicated that you are withdrawn by this exam, okay? Now you are, say, at the last year of your, say, career as a student, okay? So you will be able to judge yourself what you written, about your answering, etc. Okay, so this means that please don't let me correct a written test, your examination, and then, for example, the typical situation is this one. Okay, I correct the examination. Okay, and then I put, I don't know, 26. The students say, okay, 26 for me is not enough. I'd like to get for my average, for whatever, because I have a grant and then I need two specific threshold for my examination grade, whatever. I needed at least 28. Okay. Basically, you are able to judge, self-judge what you've written, okay? If your examination is not exactly what you are expected, don't trust, okay, and don't complain with if my grade is not so high as your expectation are, okay? So maybe in that situation, it's better to withdraw before letting me to correct your examination, okay? This happens, say, sometimes, okay, in the past, okay? And so this for me is not something which is good, okay? Okay, if you need specific value of the, maybe if you need 30, okay, the maximum possible, and you know that some questions are not good enough, so that means that you cannot get 30. So don't have the written test to be corrected and then complain to me with this, because your grade is not so high, okay? This is just for a question of, say, if you want to honesty in evaluation, okay? Try to evaluate yourself before having this, uploading the written exam. Okay, this is always all I have to say about the examination. If you have a question, of course, I can answer this question about the examination, etc., etc. I want to say that I'm available the 8th of June, which is a Tuesday, at 10 for a session of question and answer. If you want, the 8th of June at 10 a.m., which is the standard, say, scheduling of our lecture, I can start a virtual classroom in which all of you can participate in order to, let's say, have some questions about the course, okay, something which is not clear. Maybe you have time in this week for, say, start reading the material. And so basically this can be an occasion for you to ask me for something which is not clear. It's a collective, let's say, question and answer session, if you want. Okay, I can put this as something that I can do. You can receive as a standard lecture, for example, the invitation for having this question and answer, if it is something that can help you. Okay, the 8th of June, which is Tuesday, I think. Okay, so question and answers. By standard virtual classroom. Okay, I provide the invitation. Then if no students show up, okay, I can close immediately. Okay. The other thing that I already indicated, said to you yesterday, is to fill the questionnaire about the didactic. Okay, the Comitato Paritetico per la Didattica, CPD questionnaire you can find in your personal students page. Okay, if you have no questions, I wish that all the topics that you learn in this course will be somewhat useful for your career. Okay, I wish you all the best, and we can see in this question and answer on June the 8th or the examination. Okay.
Sorry, Professor, there are some questions.
Okay, good. I cannot hear you. No more.
No, in the chat.
Where is the chat? Because I cannot see. I'm sorry. But when I have, maybe I have to switch the camera. Let me go switch off let me this action here. Okay. Oh, okay, good. The chat is only, say, visible when I switched off the. Interesting. Antonio Mole, so the first question, should you provide some example of examination just to training a bit? Example, do you mean, say, a complete examination of previous years? Kind of. I think that some example of examination is difficult because this year is the first year that I have this kind of examination, okay? Which we have the first part, which is, let's say, 5 to 10 small questions, and then 2 open questions. So, and then the questions are all about what we have done in this course. So I don't know if this is something which is useful for you. I don't have this kind of examination. I think that if you have prepared, then you can say answer in a good answer. Antonio, kind of also old one could be good. Yes, but let me try to see something, because basically the questions are basically most of the same questions all the year. So I just put one or two questions, so maybe one of the past year examination. This can be done. Okay. Can we have Marco Cannone, can we have 1 or few days to evaluate ourselves? This can be okay, can be done. I think that 1 or few days is too much. I can have just some hours. Okay, for example, say 12 hours. Okay, something like that. Yes, before say trying to register the 1 day. Okay, the examination will end. I don't know. The examination is at 11. Okay, then the 11 of the successive day will be the end of your evaluation period, if you want. Okay. Manuel Elia, do we have to upload the answers during the exam? After its ending, Manuel Elia, when you end, at the end of 1 hour and a half is the duration of the examination. At the end, you have to upload the questions. Not just one questions by one question at the end. Okay. Okay, other questions? Yes, I have to see you uploading, of course. You have to be framed by the webcam when you do that. This is the minimum requirement. I have to be sure that it's you that upload the file. Okay, so you can only disconnect from the session after uploading the file. When I see the PDF with your name, I will check the page, the number of page with you, then you can disconnect. I just asked you to know whether I use the scanner or not. You could use the scanner in front of you. You have the scanner, the same webcam that frame you during the examination must frame you when you scan the document. Remember that there are tools that are based on the using your phones. Okay, you can have, say, scanning documents by using phones. So you don't need to, say, too large, too big scanners, or say high resolution scanner. Okay. Or you can put your scanner, say, on the desk on which you are making your written exam, or I cannot let you move for your seat to another room. Okay, this is not possible. For me, it's something that is not possible. I trust you that you are not copying or you're, but okay. Use cam scanner. Okay, good. Yes, there are a lot of that. Try the Polito app. Polito as an app which can be employed to get exactly this feature, okay? As this scanner embedded in the application, Polito app, the application of the Politecnico di Torino. Just a final question. Usually in lectures held in physical rooms, students clap their hands, thank the person there. Okay. You don't need to do that. Maybe after the examination. Okay. Okay, I'd like to thank you for your attention. Okay. And if you have no question, we can stop here. Of course, you can contact me anytime by email, by phone, or typically by email or phone. And then we can see each other in June the 8th for this session. If you have problems, you can contact me for, say, studying or whatever else. Okay. Thank you very much. See you. Have a nice day.